Welcome to the OXAI Podcast. I'm your host, Jessie, from the Oxford Artificial Intelligence Society. Today, we have the pleasure to have Professor Nick Hawes, Professor of AI and Robotics, and the Director of Oxford Robotics Institute at the University of Oxford. Thank you so much for joining us today, Nick.
It's a pleasure. Thanks for the invitation.
And before we start, congratulations for the Oxford Robotics Institute to win the Queen's Anniversary Prize on Innovation of Autonomous Robotic Technologies. That's huge.
Yeah, it was a very happy moment to get awarded it. It's on behalf of, well, like a decade or more of work for hundreds of people, really. So it kind of recognizes the work that we've done in innovation in technology, but also in policy and changing the way society thinks about robots and thinks about using them. So it recognizes a huge amount of work from a lot of people, and I think it also kind of shows the excitement that there is about this stuff in the future as well.
We are super keen to hear more about your insight during this podcast as well. And from your background, you have done extensive research in robot autonomy. What is your current focus in this field?
So my group works on decision making for autonomous systems, kind of in a very broad sense, but particularly we think about kind of autonomous robots. And our work is generally in the kind of model-based camp. So quite a lot of our work is actually taking robotics problems and finding ways to model them. And we're, in particular in that space, we're interested in problems where there's uncertainty and long horizons. So when a robot acts in the world, it's very hard to model accurately how the robot interacts with the world or how the world changes. And so we think about the uncertainty and the probability of the world changing or the robot changing in particular ways. And then we're interested in what happens when you have sequences of those interactions or sequences of those actions over anything from minutes to months. I mean, that's what distinguishes us from people doing kind of control or continuous reinforcement learning. We think about, rather than thinking about the next kind of millisecond, we think about the next month. So we're interested in
long-term planning.
Yeah, long-term planning, long-term decision making, and how you reason about uncertainty over that horizon. So that's the very big picture of what we think about.
It sounds like there's a lot of factors to take into consideration, especially when you mention uncertainty in the environment.
Mm-hmm.
I don't have much background, but I would imagine a self-driving car, even just in this specific application, there are so many factors to consider in the model. So when you work on this, how exactly is the decision-making process modeled in your work?
So we base almost everything we do on a Markov decision process. So that's kind of the fundamental part of what we do. So that is, you have a set of states which describe snapshots of the whole system. So that's snapshots of the robot. That might be the location, that might be the battery level, that might be other things about the robot. It's typically some environmental features. So that might be the positions of humans. That might be whether doors are open or closed. If we're a mobile robot indoors, that might be something about the weather. So anything you can put into a kind of a sort of snapshot of the state we think about. And in general, we think about this typically in a kind of discrete sense. So if we think about location, we're going to divide the world up into discrete locations or parts of a graph. And then mainly we do that because we want to reason about these long horizons, and doing that in a kind of continuous way is pretty tricky. And then we think about actions. So actions are the things that the robot can do to change the world. That might be, a lot of what we do involves a robot moving from A to B, right? That's the kind of most obvious for us action that a mobile robot can take. But that robot might also, pick things up, or change something less obvious, like talk to a human or try and influence a human. And then we model how those actions change the robot state. So that's kind of the key thing of a Markov decision process. You've got these states and then your actions. The actions, the action of moving from A to B will change the part of the state that describes the robot's location. But we're particularly interested in things that change in kind of uncertain fashion. So one thing that might change in an uncertain fashion is time. So if you've got a robot moving through a crowded environment, the time it takes for the robot to move from one side of the environment to the other will be governed by some probability distribution that's influenced by the number of people that are there and how they're interacting. And that then in turn might interact with the robot's battery. So the robot's energy use for that action might be uncertain. And then if you start to think about how you want to sequence together or plan together different route choices or controller choices, do I go fast or slow through that environment? That will influence the evolution of these states in uncertain ways. And then we kind of think about, okay, now we can do that. What do we want to do? Well, typically what we want to do is plan for a goal. So if you look at kind of people who do reinforcement learning, they typically want to maximize a reward, which is some number that describes how good an action or a state is. We typically have more semantically meaningful goals. So we want the robot to reach its location with 50% of its battery left, or we want the robot to deliver a parcel before 3 p.m. And we need to encode those things typically in our state, or those factors in our state. And then we want to reason about ways to guarantee that the robot can do that despite there being uncertainty in the evolution of those variables.
So if I'm understanding this correctly, does it mean it's like more constrained optimization?
Yeah, that's one of the ways of solving these things. So you typically you build your model. So we're kind of model based. So we typically have some way of writing down not necessarily the whole model, but bits of the transitions, bits of the probabilities, or we have ways of sampling those from learnt models or from simulations. And then you say, okay, achieve this state in a way, achieve this state such that battery level doesn't exceed this. Or so you've kind of got the thing you're trying to achieve, you've got some constraints on that, and then the algorithms we build or use from the literature are kind of optimizing a policy to achieve that goal. So there's absolutely kind of a constrained optimization. And then sometimes you might do it under constraints. Sometimes you might do it in a multi-objective fashion. Sometimes you might do it in a probabilistic, maximize probability that this happens. So yeah, you can absolutely think of it as optimization running on a model where that model describes states and actions and transition probabilities.
That sounds really cool. This might be a dumb question from me.
There's no such thing as dumb.
But what if, like, for example, you mentioned about long-term planning. For example, like we're training the robot to kind of like maximize this reward function or like some other objective function according to some constraint. What if in the middle of this training there's some new state came out? For example, for the robot, once it's moved to a new space, there might be some other action you can consider.
Yeah. So this is, in terms of kind of the first question, we said, what's our focus? So actually our focus in the research is often around the fact that you cannot really write these models down clearly in advance. So there's this whole area of reinforcement learning that thinks about effectively having no access to a model, or having to learn that model. We tend to do a bit of both. So we tend to try and define as much of the model as we can, but also involve some observation or some learning online. So typically what happens for us is there are things that we know that we don't know at the start at planning time. So you said train. We don't typically train our systems, we plan. So the robot has some model, some simulator, some generative model. It samples or iterates through that to build a policy. But then we often act in an online planning fashion or a receding horizon fashion. So the robot will take some actions, maybe it'll walk around the environment, and then it will find that a door is open when it thought it was closed, or it might find that its battery has gone down much slower than it thought. And that means that parts of the environment that were previously unmodeled or unavailable, or parts of the state space that are unmodeled, then become accessible to the robot. So we often rebuild the models online. So traditionally when people do this stuff, they write the model all down in a text file and give it to an algorithm. We generate the models programmatically from the robot's observations or from other data sources like a 3D map, for example. And that means that online we can reconstruct bits of the model or generate new bits of the model as we go. So we don't typically add like new actions. There wouldn't be a new type of action. The robot's kind of suite of actions is fixed, but there'll be new states reachable in some model that weren't available at the start. So yeah, I guess the answer is online planning with some observations. Right. And the interesting question is so one of the open questions for us, so this, I'm slightly wittering. This is epistemic uncertainty. So we have not only uncertainty in the robot's actions, we have uncertainty over the model. And we know that as we act, we can reduce that uncertainty. But we want to plan to do that. So we'd like the robot to have some distribution, some prior over the fact that these new bits of the world might be available, and that might change the robot's behavior. So we also want to kind of represent our uncertainty over our own knowledge of our model, and that's where things get super interesting about kind of robustness and risk.
So it sounds like it's like a real defined problem to begin with, and then you mentioned use online learning technique to make sure the model updates itself based on the new input from either environment or action space.
Yeah, absolutely. So we use things like Gaussian processes to model parts of that belief, or we might just sort of do some filtering with some kind of a particle filter or something. So you have an explicit belief representation, but if you can do something in a closed form, then you can reason about how it evolves given future observations.
So the next question is, what are the practical applications of robotics in your work? And what do you think will be the next big application?
So the practical applications, practical applications of robotics are massive. We've seen particularly kind of automation change factory work and things like that. I think we're now at the point, I think it's probably even like the third wave of a kind of robotics revolution. The second wave was robotics working autonomously rather than just automatically, but in very controlled environments. So if you look at Ocado, you look at Amazon, those kind of warehouse problems are kind of solved, right? The robots are more autonomous than, say, a car factory robot, but they're operating in a world that's incredibly predictable and structured. The thing that's interesting now in terms of applications is moving out of that structure into unstructured environments. And people need robots, particularly for things like labor shortages. If you look at kind of delivery, you look at cooking, you look at agriculture, these are places where we have jobs that need doing, but we don't have the humans to do those jobs, or humans don't want to do those jobs. And so these are tasks where you would ideally use a robot, but the actual environments are not as predictable and structured as something like a warehouse or a factory. So there's huge kind of, I think, practical applications there, because these environments are still reasonably well structured. A field, a row of berry plants is kind of similar to some other row of berry plants. So it's not completely unknown. And the same with kind of logistics work, driving, things like that. There's enough structure that we can exploit them in our models and learning, just like any kind of AI style problem. We need a bit of structure. We need to know what kind of tasks we're dealing with. And then we can kind of work in those spaces. So I think the applications now are people are looking at where can we support like the existing workforce and use robotics in places where there's a greater degree of variability in the world, but also a need to kind of address that variability.
Do you think the current progress in AI can be of any support for that?
Yeah,
For example, the generative models, etc.
So absolutely. I think how we do that is still quite open, and particularly on things like foundational models. But the sort of the deep AI revolution in computer vision, in reinforcement learning control, has completely changed what is possible in robotics. I mean, it is still the case that every month at least I see something and go, oh my God, I didn't believe that would be possible. And the reason that is interesting is exactly this kind of previous statement about moving to less structured environments. We have to be able to cope with, or our robots have to be able to cope with a greater degree of variability across environments and across tasks. And the only way to do that we know of that works well now is through the application of data-driven methods, machine learning methods. So there really is, I think, a great opportunity to move to this space. And in the world that I work in kind of decision making, again, people are super sort of excited by large models, large language model style things, these kind of transformers that are super robust to general inputs. So historically, when I started in this field in the noughties, a long time ago, we would write planning models and decision models by hand, and they would say, the robot has a pickup action and it can pick up mugs and boxes, and then you would map a mug and a box to a classifier, and everything would work and you get this lovely behavior, but it would be super, super brittle. You change the objects you were working with, you change the task, and everything would just break. You look at the kind of things that AI can do today and you go, wow, this stuff is now very robust to at least a wide variety of inputs in individual modalities and in individual time slots. How you put that all together in a way that makes a robust series of actions is still quite an open question, I think. I think there's been some cool work with kind of like the Google teams, for example, building robots that are using kind of transformer models, but it still feels like we're just kind of scratching the surface, and we're probably getting the worst of both worlds at the moment. We're not really actually integrating these things properly. I think it's kind of, there are still some interesting dividing lines that we don't know how to bridge between the kind of hard, real-time physical constraints of robotics that can't break, and these kind of open-ended hallucination generative models that can kind of imagine anything and will tell your robot to do stuff that's physically impossible. So how you ground this kind of generative space in this physically constrained space is very much I think an open question, and there are a large number of roboticists working in that space.
Do you think this will be the next big like innovation? This is where the next big innovation is going to come from in robotics.
I think so. I mean, it seems very. It would be strange to bet against that being the case. I mean, there are a lot of very smart people working in kind of machine learning for robotics and applying these kind of generative AI and kind of foundation models to robots. I think it's also the case in terms of the field. It's getting harder and harder to publish papers and get kind of people excited about more traditional methods. So the students, the new grad students, new PhD students that come in also want to work in that space because that's where the kind of excitement is right now as well. So I think the robotics as a field is just moving closer and closer to machine learning anyway. I mean, it always was. Like robotics and machine learning have always gone hand in hand. People have always realized that data-driven methods are kind of the way to solve a lot of these problems. But I think increasingly people now only look to those methods in
So you mentioned about like the one constraint, like one challenge about applying this large machine learning model to robotics is that like the model is not fully developed yet. There might be some like it's kind of hard to apply this model to the physical constraint world.
Yeah.
Is there any other challenge you would see in applying this method to robotics?
I think one that a few of my friends are working on that I think is super interesting is what is the kind of prompt equivalent for a physical system. So in a language-based system, you can kind of set the problem through text. So you describe, okay, I want you to write me a short story about this, and I want you to do it in the style of a pirate or whatever, and then off you go. And the model there has all of the prior information in text and does all of its actions in text.
Mm-hmm.
In a robot, right, you've got a mixture of the semantic, symbolic stuff. So maybe I want the robot to fold this T-shirt, to use a topical example, and I want to do it in a particular way, which I might be able to describe by text. But then the robot has to kind of prompt its model as well by looking at the world. Where is the T-shirt? What limbs have I got? How close am I to it? So there's a lot of this kind of physical or multimodal information that you need to get into the model, as well as the semantic stuff. So how do you, for a particular task, so like this is an execution time or a test time, how do you kind of prompt these large models to understand the world, or how do you initialize their latent spaces, or what are the correct latent space representations to use in order to be able to reason maybe in a more kind of crisp way? I think these are all kind of interesting questions. So the initial ideas are always like language is kind of the lingua franca for talking between all these points, but that is just not the right way to do it necessarily for robots. But I don't think people are really clear on what the right way is. So yeah.
Well, I guess it's such a large field to explore at the moment. So
Yeah.
just a random idea, because a lot of people mention using this like generative model to write code. Do you think it would be possible to use, like, for example, a large language model to write code as a part of the long-term planning?
Yeah, I mean, people are doing this for robots already. So there's work out of Microsoft, for example, that are using their large code models to generate controllers for robots. And so rather than going language to language, you kind of go language to code, and you've got the code that can write parts of the robot controller. There was an example which was about using code. I can't remember whose work it was though. It was someone outside of Oxford. But using the code generative model to write a reward function. So training the robot by giving different reward functions, because reward engineering is a huge part of what people do in like machine learning for robotics. So these kind of generative code models seem very powerful in that sense, and they give you a more expressive or more appropriate quantitative way of thinking about interacting with the robot. And they are checkable, right? You can analyze them, you can verify code in a way that is hard to do with language. So absolutely, it's a great idea. People are starting to look in that direction.
In your research group, you do a lot of research on alternative robotics. Is there any different opportunity in your research group, and what skill set do people should have in 2024 if you would like to work in this field?
Yeah, well, thanks for asking. So yeah, we're always looking for great DPhil students. We're advertising a studentship at the moment, which is to work on long-term decision making for a mobile robot in a nuclear context. So we're partnered with a company that used to be named as Magnox. They're now the Nuclear Restoration Services company. So they deal with decommissioning of large nuclear sites, and we've been working with them to use a quadruped, so a Boston Dynamics Spot, to do large-scale inspections of their sites, because a lot of kind of infrastructure companies want to monitor their facilities and check that if there's been a storm, it hasn't knocked down a set of pipes or something, and you want to have a robot repeatedly image these environments. So the problem we're solving is how do you deploy a robot in a setting like that where there's very limited network, very limited Wi-Fi, because these companies want reliable networking to get data off the robot and to be able to control the robot for recovery action. So one of the key uncertainties in that kind of planning problem is access to the network, and then kind of thinking about how access to the network changes the success rates of other actions. So we have a 3.5-year PhD studentship to work on that. And I think it closes March 1st. So if you're listening to this before March 1st and you're interested, please do apply or get in touch. What skills do people need? It's a really interesting question. I think about this a lot. So they need to be able to code. Like everything we do is coding at some level. We don't necessarily, in my group, you don't necessarily need to have any experience with robotics, but you have to be willing to be excited by them and constrained by what you can do in the next 10 years with robots. That's kind of the way we think. We want to generate AI systems for future robots. You need to be able to think about maths. So maths is key to everything in AI, right? You can't just slap together a few bits of Python and go, I've done research. You need to be able to understand the mathematical and formal underpinnings. But I think the key skill is abstraction. So when I think about what I want my students to learn, particularly, I don't know how relevant this is to other bits of AI, but in robotics, it's key. So we think about the world at multiple levels of abstraction. We think about the controllers that the robot is running to actually move its limbs or its wheels and estimate its state and location. And they may be running at 10, 15, 30 hertz. So these are things running very quickly, traditional bits of software in the robot. And then you've got other processes that run in the robot and in the decision-making systems at different frequencies. So some of these kind of planning systems, say if you're doing a motion planner, that might run a couple of times, once a second or every 3 or 4 seconds. And the decision-making system might not change an action for a couple of minutes. And all of these kind of layers build on top of each other. And I think the best robotics PhD students that I've worked with are able to sort of understand that hierarchy and choose the right level of abstraction to work at and kind of build their models or plan their research with a knowledge of this rich hierarchy, but fit in somewhere. The students that I think struggle in robotics PhDs particularly are either completely overwhelmed by this kind of variety of approaches or aren't able to necessarily correctly position their work in that hierarchy. So this is kind of in some sense classic computer science, classic systems engineering. You have to be able to abstract away from the unnecessary detail, whether that's fine-grained detail or big picture detail, and kind of build the right kind of model of the world. And that's kind of in your head rather than the computer, right? You have to be able to understand the world. So the ability to get the right level of abstraction, I think, is key. How you train that, I don't know. I'm not even sure I know how to select for it, but it's something that I think is important.
It's probably something comes with years of experience.
Yeah, absolutely. Yes, I think that's true.
Yeah, we'll definitely share this opportunity in the caption as well. If you're interested, please check out our caption. And the last question is a relatively trivial question. I have started doing this for our guest speakers. Yeah. If there is one book you'd recommend, what would it be?
Good question. So I read a lot of science fiction books, which is interesting because I don't think it's necessarily connected to my work, but they all involve kind of robots typically, which is.
Yeah, I was going to ask, is this how you get your inspiration for a new paper or a new project?
No, I think not. But that's a question I haven't answered for myself yet. There's a great series of books by an author called Martha Wells called The Murderbot Diaries. There's about 7 of them now. And this is kind of like a sort of classic sort of space opera adventure stories, but written from the perspective of a security robot who's called Murderbot. And Murderbot is like an AI system and a robot that's designed for security tasks. But the super interesting
Murderbot. That's an aggressive name.
It is, but that's kind of a joke because they've got a really, really bad reputation in this world. But this Murderbot has kind of unhooked its governor module. So the governor module means it has to do anything that a human tells it. But this robot has kind of unhooked that somehow and spends the whole time reflecting on why humans do particular things. So the robot just doesn't understand its environment. And it can model human behavior and it can kind of understand patterns and kind of understand the world. But it's written from the perspective of a kind of neurodivergent human, effectively, that is aware of all these things happening, but is unable to necessarily understand their own feelings or the way people behave in the world. So it's a fascinating kind of way of thinking about a very advanced AI system that's embedded in a human world, but doesn't fully understand the world. And the final sort of twist to it is the way that that robot learns about humans is by watching sitcoms and TV programs. So it kind of continually streams like adventure programs in its own head. And that's how it relaxes, because it can kind of control and predict TV, because TV follows certain rules. So that AI system is like going, okay, I can predict the future of this kind of, I think it's called Adventures of Sanctuary Moon, which is like the fake TV program in the book. And because it's so formulaic, it helps that robot relax, because it's easy to predict. But when it goes out in the real world, it gets tense and nervous, because like the world is full of actual humans that are very hard to understand. So Murderbot Diaries, Martha Wells, brilliant series of books.
Thank you so much for the recommendation. I will definitely super keen to get a copy of this. Right. Thank you so much for joining us today, Nick, and thank you so much for your time.
Cool. Well, thank you very much, Jesse. It's been great.